Yes, it started right now.
Okay, great. So let's start with a brief reminder of what was in this exercise. So we said there were these different parts. The first part was about using Plumed directly from Python. The second part was about constructing these chemiscope representations using this nice tool that these people in Michele Ceriotti's group have developed for doing these things. The third part was then this dimensionality reduction stuff, so using Plume to construct various representations of the data using PCA, MDS, and SketchMap. Then we sort of went into a sort of systematic way of constructing these collective variables. So for using these path collective variables, so we looked at the distances from configurations, and then we saw what we could do with this idea. And then the last part was on introducing this business of indistinguishability. So if we've got atoms that are symmetrically the same, we have order parameters, we have lots of these order parameters. How do we then get out information and construct collective variables in a way that's sympathetic to the fact that certain atoms, if we change the labels on them, it doesn't really matter, and we should take that into account when we build our CV. So that's everything that was in that exercises. As we were talking about, you didn't have to do all of it. Some of it might be more relevant to your research. Other parts of it might be less relevant to your research, and it's fine and understandable if you choose not to do those parts. So what we'll do is we'll go through the various exercises, we'll fill in the blanks in the plumed inputs. After this session is finished, I have everything in Python notebooks, which I will upload onto the GitHub. So if there were parts that you didn't do, if there were bits that you didn't get, that you got stuck on, you can look at those, okay? But I don't want to spend a lot of time talking through Python because I don't think that's going to be particularly useful to you. It's more useful to look at those exercises. And if there are things that you don't understand, by all means do keep asking, because it's not as if you can't ask after the session, after the 2 weeks is over. Okay, so without further ado, let's get on to some screen sharing, and let's have a look at these exercises. So it should be that one. Okay, so here are, this is a Python notebook. What I did is I copy and pasted into here all of the input files that had blank spaces in. So we're going to talk through how to fill in the blank spaces in those input files. In exercises 1 and 2, so the exercise that was about calling Plume from Python, and the exercise that was about introducing you to Chemiscope, there were no blank spaces in those input, there were no Plume files with blank spaces in. So there's nothing in that section, and you just look at how the example notebooks work if you're interested in using those methods. Okay, so I'm not going to talk about that because you can look at it in the notebook file. So let's, God, I hate this thing at times. Let's have a look at this. Why does it do that? Okay. Okay, great. So this is the first input here. And what this is going to, does anyone know? So if we think about this, it collects data from a trajectory. It's written in the notebook. Okay, so this is going to collect the data for later analysis with our dimensionality reduction algorithm. So this is different from how Plumed works normally. So how does Plumed work normally? What's the difference for this sort of input from what Plume would normally be doing when you're doing, say, a metadynamics calculation or a umbrella sampling, or just doing the sorts of analysis that you did in week 1 of this course? What's different when we do a dimensionality reduction algorithm?
We need to store all the frames.
We need to, exactly, we need to store all the frames. And why do we need to store all the frames?
Because we need all the points?
Yeah, because we need multiple points in order to construct one of these dimensionality reduction representations. So great. So we've got this input file. Does anyone know what goes in for this to replace this first fill here? What's the name of the template file in this case? People said they did the dimensionality reduction algorithm.
Is it bhp.pdb?
Yes, it's bhp.pdb. Okay. Is it
bhp?
P? Yes, bhp. Okay. So what goes in there is bhp.pdb. What purpose is this structure? What structure is this? Purpose is this bhp.pdb serving in that command there? Molinfo. What does molinfo do?
Reference to read the trajectory, the reference structure to read the trajectory.
It's a reference structure, okay. And why is the reference structure useful here?
Like we need to tell the Plumed that this is the structure to look for when you are reading the frames in the trajectory.
Okay, we're telling us to this structure to look for. Is this like, okay, so there's different types of reference structure. Is this like how we would define a reference structure when we calculate an RMSD?
No, it's has to do with topology because we want to use the at non-hydrogens in the next line.
Yeah, so basically what this is doing here is it's defining various important groups of atoms that we can then use as shortcuts in other commands that appear later in the input. Okay, great. So next fill in here, that's the keyword. So what's the keyword that goes in here?
I think it should be protein.
Are you sure?
Probably not.
Maybe atoms.
Yeah, I think it's atoms as well. So it's atoms that goes in there. It's telling us that what we're going to do is we're going to collect the positions of the non-hydrogen atoms. Great. Okay, and then we've got one more fill here to put in. So we want to output all the data that we've collected from the trajectory to a PDB file. So where is the data that we've collected that we want to output? What's the label of that data in that input?
CC.
Yep, someone?
CC.
It's CC, exactly. So it's going to be the label of this collect atoms object. How many frames are there going to be in that traj.pdb file? You don't have to give me a number. You have to sort of give me a description of how many frames there are going to be.
All the frames, because there is no stride.
Exactly. All of the frames from the trajectory that you read in will be output in that traj.pdb file. And will you output all of the atoms that are in all of the frames in that file?
No, just the non-hydrogen.
Just the non-hydrogen atoms. Okay, so we sort of understand the idea there. Okay, anyone got any questions about that? So that's how we do this other mode of running within Plumed, where we collect the data and then we go and we analyze it later. So now let's go talk about how we're going to run a PCA calculation. So this is the input for PCA. So what goes in, this one is easy. What goes in there? It's not a trick question. I can see you dying to say it, Isabel.
The same from above, like the PDB name.
bhp.pdb. Okay. What goes in here? Raphael? Atoms. Brilliant. And what goes in here? I'm going to move CC, fantastic. Okay. So project all analysis, that's exciting. Oh yeah, project all analysis data, use output data from, what goes in there in this first fill on this line?
Also CC.
Also CC, excellent. And what about in here for projection?
PCA.
PCA, fantastic. And then output analysis data to carve file, use output data from, oh, there's a choice in here. Which one did you pick? That's
PCA?
DAT.
I think it's DAT. Yeah, I think you're right. It's DAT there. Okay. That's a curiosity of how this is implemented within this method. Okay, so when we do this here, when we use PCA or any one of these methods, we're measuring the distances between frames in the trajectory. How are we measuring the distances? What method are we using to measure the distances between frames in the trajectory here? How do we define this is the distance between this configuration and this other configuration?
Could you maybe repeat the question, please?
Okay, yeah. So when we use one of these dimensionality reduction methods, we collect all this data from the trajectory about the various configurations that have been sampled, and then we need to measure distances between those configurations. So how are we calculating distances between configurations here in this input? What are we?
Sorry. Go.
Did I cut out?
I think someone else was trying to answer, but I'm
Oh.
not sure. Anyway, you calculated in PCA space, I guess. So you have 2 dimensions in 2 PCA coordinates, principal coordinates, and you calculate the distance between the points.
Okay, not really, no.
Okay.
So that's what you do later. So you get out these 2 principal components later, but before you do any of that, when you do this principal components, you're calculating the covariance. So does anyone know what's the size of the covariance? So PCA, basically, we calculate the covariance, and then we diagonalize that thing. So the covariance matrix is a square matrix. So does anyone know what the shape of that matrix is? How many eigenvalues it has?
The number of frames.
Shouldn't it be the number of features, like the variables we use?
Yeah, so it's the number of features. So how many features do we have here?
The number of non-hydrogen.
Okay, the number of non-hydrogen. So the number of non-hydrogen atoms. Any variation on that? That's not quite right, but we're getting there.
3 times that.
3 times that. Where does the 3 times come from?
3 dimensions.
Spaces.
For each atom.
Yeah, because space is 3-dimensional. So we have positions of each of the atoms. So this covariance matrix is measuring. So when we measure the distance between 2 points, we're calculating how far all of the atoms have moved. Okay, but we've seen this idea before. We've seen this idea of calculating how far each of the atoms have moved, and we've seen that there are certain problems with doing that. and that there are tricks that we can do to resolve those problems. So does anyone remember what are those tricks? And I'm going to highlight something in this input file that might help you. What's the significance of this word optimal here? Where have we seen that before? In what context? Okay, let's go pick someone. Maria, are you there? Do you remember where we've seen optimal before?
Yeah, I'm here, but I don't have a clue. I'm sorry.
Not to worry. Kiara, is that right? Okay.
I think in the second masterclass, but I don't remember where.
Okay, so we're in the second master class. Okay, great. I don't know if it was in the second master class, but
No, I wasn't.
I don't know if we covered optimal in the second master class, but good for having a go. Lorenzo, any ideas?
In the RMSD.
In the RMSD, yeah. So, you know, when I
Okay.
answer, you know the answer. When I ask questions, you know the answer. Dive in and answer. So in the RMSD, and what was the significance of that word optimal in the context of RMSD? What did that optimal mean we were doing?
It refers to the translation on the system.
Okay, it refers to the translation of the system. Okay, that's one of the things that it refers to. What does it tell us to do about the translation of the system?
That it performs a translation and a rotation on the system rather than just simple translations.
Okay, so yeah,
It's significant changes in the structure.
yes, it's changes internally in the structure. So we move we're removing the rigid motion. So we rotate one structure, we translate the structure on top of the other, and then we rotate it into the same frame, and then we look at how far all the atoms have moved. Yeah, because otherwise the movement of the atoms comes from just basically rigid translations and rigid rotations of the molecule. So what we're seeing is an idea that we saw somewhere else in the context of RMSD, reappearing now in the context of PCA. Okay, is everyone happy with that idea? Anyone got any questions before we move on? Okay, silence, it's fine, move on. So let's go on to this next one here. Let's just, okay, so there we've done the mol info here. So we've now got all of these things to fill in. So let's go through here. So what goes in here? What's in this fill for RT4 phi, do we think? What goes there? That one's very easy. Simon?
Atoms equals at phi 4.
At phi 4, perfect. And the next one, Maria. Oh God, I've already started typing it for you.
Atoms equals at psi 4.
Yeah. And the next one, Salman.
Atoms equal phi 5.
At
At the rate 5.
At phi 5, exactly. And we're not going to do all of those because it gets super boring super quickly. We're just going to skip straight to the last one and go to someone who hasn't spoken yet. Stefano, have you said something?
No.
Give me this
So-
last one here.
would the atoms equal at psi 16?
Exactly. Okay, great. So there we go. Okay, so now we've got this collect frames, okay, that we've seen before. What goes in here? Martina.
ARG.
ARG, yes. Why is this not atoms, Martina?
Because they are not atoms, so I have to put arguments instead.
Yeah, very good, good answer. So these are not atoms, these are arguments. Brilliant. Okay, so now we've got this Euclidean dissimilarities matrix. What are we using? We're using the data output from what? Beatrice?
Angles?
Angles, yeah. And how do you pronounce your name, sorry?
Beatriz.
Beatriz, okay. Yeah. So is that Spanish?
Yes.
Okay, I should have known that. Sorry about that. Okay, great. So then we've got a landmark select FPS, okay? And what's coming in to our landmark select FPS? Federica. Distmat, excellent. And then we're going to do classical MDS, okay? And what is, that's a good question. What is going in for this fill here? Irene?
Hi.
Hi.
Well, I put use output data. I think, well, sorry. Yeah, I did. Yes.
Is it just use output data or is there another word on there?
Sorry, from.
Yeah, brilliant. Okay, so that's use output data from FPS, the one above. Okay, brilliant. Then we're nearly there. So now we've got project all analysis data. So what's going in? What are we projecting? What data are we projecting? Ivia? Oh, no, I think there's stuff missing. Oh, Olivier.
Distmat?
Yep. Brilliant. Oh, sorry. And what projection are we using? Simon?
I'm not sure.
Okay, that's fine. Good for admitting. Salman, what projection are we using there on that line?
I'm not sure either.
Okay.
MDS.
Okay, great. Mystery voice. Thank you very much. I think it was actually Oscar.
Yes. Hi.
So it's MDS. We'll come back to that line and talk about that in a moment. So then we've got this output analysis data to Colvar. What data do we think we want to output? Isabel, because you had your hand up a minute ago. She's like, oh, I had my hand up for the question I knew the answer to, and now you've asked me the question I don't know.
I think it's MDS.
Are you sure? We want to output all of the data.
Oh, sorry, then it's O sample. So to have all.
Exactly.
Sorry, yeah.
No problem. Okay, great. So then that's our whole input filled in. I think there's nothing else to fill in there. Other than all these, which I'm not doing because it's just too boring for words. Okay, so here we've collected all the data. And we've calculated this dissimilarity matrix distmat. So this is again, it's a square matrix. How big is this matrix? So how many rows or how many columns does this matrix have?
That's equal to the number of frames in the system, I think.
Yeah, so this is it's a number of frames by the number of frames, because inside each element of that matrix is the distance between frame I and frame J. So if we think about matrices, we learn all sorts of wonderful descriptions of matrices when we were doing our undergraduate. So we learned about things that are matrices that are unitary. We learned about matrices that are symplectic. We learned about matrices that are other types of symmetries within there. So does anyone know what type of matrix is this matrix here, distmat? It's square and it's also
symmetrical.
It's symmetrical. Yes. So what does it mean when we say that a metric is symmetric?
That the element at the position 1, 2 is equal to the element at the position 2, 1.
Yeah. Okay. So all of the elements. So it has a mirror plane along the diagonal. If this is the matrix of dissimilarities between configurations, what are all of the diagonal elements of the matrix equal to? Someone who isn't, I'm sorry, whoever the mystery voice was. What are all the elements, not you, someone else, just to give someone else a chance?
They should be all 0.
They should all be 0 because the distance between a configuration in itself is nothing. Okay, so we've got this matrix here where we calculate all these distances. Then what are we doing on this line, this one with landmark select?
And reselecting 500 random points from this dissimilarity matrix.
Yeah, so we're selecting 500 points. And why do we do that? Does anyone know why we select 500 points rather than working with all the points?
Because it's easier.
Okay, why is it easier? What do we mean by easier?
Like not that heavy for the machine because you don't want to fit all the data into memory, very likely.
Yeah, so it's, well, we have all the, okay, yeah. Okay, so it's not just memory, it's also computing power. It costs a lot more for us to diagonalize a 1000 by 1000 matrix than it does a 500 by 500 matrix. So if we can make that matrix a bit smaller. So within this landmark select command, we've got this FPS. Does anyone know what FPS means?
Farthest point sampling.
Farthest point sampling. What do we do when we do farthest point sampling?
It's like a maximum distance algorithm where you are starting to pick the next point as far as you can actually have.
Yeah. So it makes all our points as spread out across the space as possible that we can get. Okay, so that's our farthest point sampling. Then we do this classical MDS, which is diagonalizing that matrix. And then this project all analysis data says basically now once you've got this one, project all the non-landmark points. Okay, so we do have all of the points in the trajectory at the end of the input. Okay. So at the end of this file, we've outputted these various alpha RMSD, anti-beta RMSD, and so on and so forth, as well as all of these projections. Why are we outputting these numbers at the end of the output file? What's the point of outputting these alpha RMSD, anti-beta RMSD, and so on in context?
Is it because we want to color them later in Chemiscope?
Yeah, so we're going to color it according to these things in Chemiscope. And why are we going to color it according to those things in Chemiscope?
To look for a connection.
Yeah, Yep. I mean, it's to make sense of what we're seeing. Okay, so this is not, the coordinates that we get out of this dimensionality reduction algorithm, they're not physically intuitive like, say, an alpha RMSD is. We know that when the alpha RMSD is big, we've got lots of alpha helix in the protein, and when it's small, we've not got much alpha helix in the protein. So if we plot a graph of, I don't know, configuration on the y, alpha RMSD on the y-axis, along that line, but we can't do that if we can't do that with we can't say that we don't have that same physical insight into these dimensionality reduction coordinates. So we also print out these quantities so that we can make sense of them. Okay. By the way, my computer has just told me that my internet connection is unstable. So if I cut out, can someone dive in and tell me that I'm cutting out? Can you hear me?
Yeah, so far it's fine. It was just some lag time, but it's okay.
Okay, great. So I hope no one has any questions about this MDS one. Nope. Okay, so we can go on to the next thing in this one here, which is sketch map. Is it useful to go through, because this one is very similar to the previous one. So I think I'm going to skip that unless anyone desperately wants me to go through this.
No, I actually have another question regarding the SketchMap algorithm. Is there a Python implementation for SketchMap in terms of if we don't want to use Plumed, which is silly to ask in a Plumed tutorial?
No. There is the original SketchMap code which you can try and use as well, so that's available. But a slight problem with SketchMap compared to some of these other algorithms in dimensionality reduction is you've got a lot of hyperparameters. So you've got 5 hyperparameters for this thing. So there's a lot of messing around in setting those parameters, and this sort of puts people off.
Okay.
So there's this SketchMap implementation which I did. Sorry, this Plumed implementation, but I don't know if the Python implementation will be coming anytime soon. Okay. I know that Michele Ceriati, who also wrote this algorithm with me, they're working on some new, more a representation, a version of these that's like scikit-learn, but I don't think they've got plans to do SketchMap within there. So okay. Sorry about that.
Okay. Yeah, I'm just asking because I'm doing all the other stuff in Python and it would be convenient to do the same.
So, I mean, you can do it, you can try and hide the Plumed as much as possible by using it, using the Python interface.
Yeah.
So if you're interested, we can talk about that at some other stage.
Thanks, yeah.
Okay, great. So we're going to skip that one and go straight onto the old path collective variables now. So we've kind of finished dimensionality reduction. So we're going to go on to path collective variables. So here we're calculating 2 RMSD distances from these 2 configurations. So what goes in this fill here? Raphael?
No clue.
No clue. Okay, fair enough, no problem. Olivia? Yeah, disappeared.
It should be more structure or something like that.
It should be structure or something like that. Yeah, okay.
It should be reference, I think.
It's reference, yes, exactly. Sorry, whoever that was. Here it also is reference. And what about here? What type are we going to do?
Optimal again?
Optimal, yes. Okay.
I
So
have
that's
a
our, pardon?
Hi, I have a question on that. When is actually useful to use simple rather than optimal?
Okay, good question. So suppose that you've got a ligand inside a cavity. And you want to, so basically you align the cavity somehow within the, so you align the protein and the molecule within that to some reference structure. You project the protein in the reference structure as in the frame of the molecule. And then you might be interested in the rotation within the cavity. You might also be interested in the translation in that case. So that's not a very useful example, is it? But basically, unless you, if you want to, so another example would be, suppose that you're looking at in a solution, and for some reason your solution is anisotropic. This is very unlikely. So you're interested in orientational changes. I can't think of an example on the top of my head, sorry. That's very sensible. It's a very rare case. That's what I would say. Is that okay?
Thank you.
No problem. Yeah, that was great. Okay, so here. So then we've got this dot product CV, which is this one. So it's this image that's in the, I'm going to skip that one and go straight to this PCA vase. Okay, so what goes here?
Reference.
Reference again. And here?
Type.
Type. Okay, great. And this is, so what's this input doing when we do this PCA vase here? Does anyone know?
You project on the PCA eigenvectors, right?
Mm-hmm. So we project on the PCA eigenvectors. What are we projecting on the PCA eigenvectors? So so we've got an eigenvector here. How many components are there in that eigenvector? So it's a vector. So what's the length of that vector?
Three times the number of atoms, I think.
Yeah, it's 3 times the number of atoms, okay? And then we've got a vector here that we project onto that eigenvector. And what does that vector measure? What is that vector? What does it represent?
The projection?
No, it's only the projection once we've calculated the projection. So if we think about that vector, so the vector tells us it connects 2 points, okay? So what 2 points does it connect?
It connects the X, Y, and Z position of each atom to the new space we defined by the eigenvectors defined by the PCA.
Okay, so it takes the first point, so it takes some reference configuration, okay, which we call the origin, and it takes the instantaneous configuration, and it tells me what's the vector that I have to move along to go from this instantaneous configuration to this, sorry, from the instantaneous configuration to the origin, or vice versa. Okay, and that's what that tells us. Now, are we just calculating, when we calculate that reference, are we just saying you move this atom by this distance, this atom in the X direction, by this distance in the Y direction, by this distance in the Z direction, or is there something else going on?
No, you multiply, I think, no?
No.
Yeah, and you also remove the first 6 principal components because those are rotation and translation of your molecule?
The first 6 principal components are not rotation and translation, and we're not going to calculate. We're not really going to calculate the first 6 components are not rotation and translation. We would have to do some change of reference in order to get that information out. But that's the right idea, is that we remove the rotation and translation before we calculate that vector that connects our reference configuration to our current configuration. So if you want, what we do is we've got our reference configuration, and we remove the rotation and translation so that they're in the same frame and the center of mass position is the same, and then we calculate how far all the positions have moved. That's what that optimal thing means. So we've got the vector that connects the instantaneous configuration to the origin. We've got the eigenvector. How do we get a single number from those 2 vectors, a single scalar quantity from those 2 vectors that is our projection? What operation do we do?
Dot product?
Yeah, we do the dot product at that stage between the eigenvector and the other vector we talked about. Okay, so this next one is very simple. I'm going to do it for you. That's reference, and that is type again. Okay, what's the difference between this one, this input, and this input?
I mean the reference that you are using for setting the differences, right?
Yeah. The reference configuration actually in both of those structures is the same. So based on the exercise, what was the difference between this, where the coordinates calculated this way and the coordinates calculated that way?
The PCA2 reference.pdb file also contains the transition state in its structure file, I think, no?
Yeah, so this one we're calculating the projections on 2 eigenvectors, and this one we're calculating the projection on only 1 eigenvector. Or one, I mean, an eigenvector is even a strong word. Here we're calculating the projection on a single vector, and here we're calculating projection on 2 vectors. And as you rightly point out, in this second case, the 2 vectors we're using are the vector connecting the initial configuration to the transition state, and then the second vector connects the transition state to the second configuration that we're interested in, the C7AQ and the C7AX, EQ and AX. Okay, great. So now we've got to this path collective variable. So what goes in here? What's the keyword? Let's get someone. Martina?
Reference.
Reference, exactly. And let's go Martina again. What's the type?
I think optimal.
It is optimal. Okay. And that's our input for path collective variables. Okay. So anyone got any questions about those path collective variables? They're sort of explained within the text of the exercise, their formulas. So maybe that's the most useful way to understand them, to have a sitting down and a think about them.
Maybe really quick, how do you get this so if you don't have this alanine path.pdb, how do you get this? Do you need special methods for that?
So what you can do is you can start off by just creating a bunch of configurations. So you can if you know what your initial and final states are, you can basically do a linear path between the two. So you calculate the vector between the two, the initial configuration and the final configuration, and you generate a series of evenly spaced points between them, and that's your initial path. And then what you can do is, as you run the simulations, you can update that initial path by looking at the way, how far your configurations are from that initial reference path that you put in. There are also ways of doing it with, I think there's a program that's part of GROMACS that's called like gmorph that tells you a sensible way to morph the structures. But there are tools, so there are a set of tools within Plumed that are called path tools that allow you to construct an initial sort of linear path between the two configurations. And then there's another tool that allows you to put, once you've got sort of new points, to make sure those are evenly spaced. So that's within path tools. You can have a look at that within Plumed. An interesting paper on this business of path collective variables and setting them up is a one by Enzing and co-workers, which is about this idea of adaptive paths. So having a path that changes shape and changes the reference configurations as you run the simulation. So that's another place to look. And within Plumed, if you look up adaptive path, that shows you how you can do the Enzing style adaptive path. And maybe you don't use the all singing, dancing version of that, but you can use some variant on that to improve and refine your path as you run the simulation. So as always, when you do these metadynamic simulations, you run the first one, you find that nothing converges, and then you refine based from there. It at least tells you something, and it tells you what you're missing. Does that sort of help?
Yeah, I think so. We should have a look probably to be sure.
Mm-hmm. I mean, what we're hoping is that these masterclasses will continue, and you know, the next sort of round will be these more, rather than doing these basic things that we're doing now, people will come and do some of this more cutting edge stuff on applying these methods to more complicated problems.
I think at some point, when I was a student, we did something called nudged elastic band. Is that something which is related to that?
It's the kind of a similar spirit. So that would be another way that you could proceed. You do a nudged elastic band method, which is a way of finding a transition state. Now, but that generally works on an energy landscape as opposed to a free energy landscape. But you could take your output from your nudged elastic band calculation, and you could use that as a path if you wanted to get the free energy, and if you thought that there was important information going on either side of the path that makes things different at higher temperature. So yeah, that would be another great way to proceed in terms of finding a path. So this comes out of, so this path collective variables comes out of a sort of a different kind of school of thought on these free energy methods, which is the sort of transition path sampling. And there's even a method called finite temperature string method, which is a variation on nudged elastic band, sort of, similar to nudged elastic band, but it works at finite temperature. So that's yet another place to look.
Okay, thanks.
Okay, great. So let's go on to this last bit, which is the ISO committer. So here we go. Torsions, Kira, I don't think we've heard from you, or Chiara, for a while.
Atoms, I think.
Exactly, and it's the same here. Brilliant.
Yeah.
PCA vars. Let's go for someone else that we haven't heard from. Federica.
Reference.
Reference. Oh God.
And I think optimal in type.
And optimal in type, exactly. And then we've got print here. So what goes here for print? Beatrice. I don't know if that was a good pronunciation.
Art
arg, exactly. And then do you know what the, for the ISO committer, do you know what the keyword is here that we want to use?
No, sorry.
Okay, that's fine. Christina, do you know what it is?
I'm not so sure.
Someone, ooh, Maria, you raised your hand.
Yeah, I found committer for that.
Committer, exactly. Which possibly has a double M in.
Yes.
Okay, brilliant. So that's committer. So what this committer is doing is we've defined each of our two basins that we're interested in, and it's basically stopping the simulation when we arrive in one of these two regions, and it's outputting to this file called basin, whether we've arrived in basin 1 or basin 2. And then we can accumulate this ISO committer stuff. But I'll put that in the Python notebook so you can see how I actually did that and how I constructed the figures and the exercise when you look through that notebook. Okay, so those are our path collective variables. And then at the end, we sort of have a comparison of these different collective variables for this particular system. And what we find is that alanine dipeptide is very simple, and pretty much every one of these collective variables is quite decent when it comes to describing that particular system. So there we go. Does anyone have any questions before we move on to this last part? I will take that silence as a no, so we can go on to doing indistinguishability. Okay, so what we've got here, the first command here is calculating the coordination numbers of all 5,184 atoms in this system of Leonard-Jones, I think, if I remember correctly. So what's the command, what fills in here? Does anyone know?
Atoms.
Oh, a good guess, but unfortunately it's not atoms.
Is it species?
It is species, yes, because we're saying that all of these atoms are one. What's special about them is that they're one species. Great. Okay. So if we define a coordination number, we need this parameter in here. Does anyone know what the name of the keyword is here?
Switch.
Switch, exactly. And that defines basically when something is in that first coordination sphere. So we're counting, so here, this command is calculating the number of atoms in the coordination sphere of each of the atoms. If we think of each of those 5,184 atoms, if we think about this coord thing, what kind of mathematical object is coord? Is it a scalar, vector, matrix, rank 2 tensor? I'll give you a clue, it's never a rank 2 tensor whenever I ask that question.
Yo creo que es...
Pardon? Oh, does anyone know? So is this a scalar, a vector?
A vector.
It's a vector. And how many components does this vector have?
As the species.
As the species. So how many components is that? Just to make sure that people are awake.
5,184.
5,100. So this is a 5,184 dimensional vector. Great, thank you very much. Okay, so this second line, FCC cubic, what goes in here?
Species again.
Species again, and in here?
Switch.
Switch, okay. What's the difference between this FCC cubic and coordination number? You don't have to be precise about the difference, but just sort of give a vague difference. If you know, any ideas that you have as to what the difference is. What are we measuring here? So if we look at the parameters of the switching function are identical. So it's still looking at something about the first coordination sphere. So what information about the first coordination sphere are we getting from this?
If the environment is similar to an FCC, let me add.
Yeah, exactly.
Structure.
If the vectors around a central atom point in the same directions as they would in the FCC cubic structure. That's basically all that thing is measuring. Okay. Great. So now we've got this M transform more data. What comes in here? Does anyone know what goes in as the input?
Cub, maybe.
Cub, exactly. It is cub. Yep. So basically, we're taking all the vector of data from FCC cubic, and we're transforming it with certain type of function. What type of function are we transforming those things by? And what's this keyword?
Maybe switch again.
Yeah, I was going to say maybe it's switch again. And then I thought to myself, but is it switch? I think it might be more than. I will look that up.
In the manual, is a switch.
In the manual, it says switch. Okay. Guess who wrote that? His name begins with G and it's not Giovanni. So yeah, that goes to show. So it is switch. Great. Thank you very much. Okay, great. So we've got this. We're applying a switching function to cub, which is a vector. So is f cub a vector or a scalar, or is it something else? So what type of mathematical object? If we apply a function to a vector, what do we get out? A scalar value function to a vector.
A vector again.
It's a vector again. Okay, so if we apply a scalar value function, we apply to a vector, we apply element-wise. So that's what happens here. Great. So then we've got this dump multicolvar. Does anyone know what that one is? Can someone look that up in the manual? Because I can't actually remember.
Data.
Data, thank you. And this one is what?
File.
File, exactly. And then we have the same thing 3 times. Okay? Brilliant. So let's go on to the next one. Okay, so I'm going to skip the first 3 lines because we did those before. So let's go on to these next 3 lines. We'll just do the first one of these because they're all the same. So what comes in here as our input to histogram? What's our first keyword?
That should be argument.
Is it argument? It should be argument. I agree with you, but I don't think it is.
Oh, okay.
Maybe that data?
It's data. Does anyone know why is it data here and not arg? What's special about this number? What is special about this thing, coord, that's coming in that means we can't use arg? What's the difference between the way that we're using histogram here and the way that we would normally be using histogram?
And coord is a vector.
Exactly. Coord is a vector, whereas when we normally use histogram, the input is what?
Arg.
Is arg, and arg, when we do arg, we're providing a list of.
Sorry, we couldn't hear your question.
Oh, when we do arg, we're providing a list of what?
Of 2 scalars.
Scalars, exactly. So here we're providing a vector. Now, when we're providing that vector, what is histogram doing? Can you hear me? Or so there are various different things that histogram could do with a vector. Does anyone? So sometimes, like in metadynamics, we have seen a vector be passed a histogram, but what happens with the histogram here is different from what happens when we pass a vector to a histogram in metadynamics.
Here it calculates the distribution of size of vectors.
Yeah, it calculates the distribution for that single number. So it's assuming that all of those 5,184 elements of that vector are identical, and it calculates the distribution for those quantities. Yeah? Does that make sense? So in the language of metadynamics, what we're doing is adding 5,184 Gaussians on every step to this histogram, except they're not Gaussians because we're using a different kernel, but we have one kernel for each of those input quantities, as opposed to just a single kernel. Does that make sense? Do we understand what I'm getting at there? I'll take that silence as a yes. Okay, so what's here? What's equal to 2? So what arguments do we need if we're going to calculate a histogram? We've seen histograms before in other tutorials. So here we need
grid min.
Grid min. Whoops. This one is
grid bin.
And this one is
kernel.
Kernel, exactly. Okay, and then we've got 2 lines underneath that are very similar. And then here we want to output that histogram. So what command do we need to output the histogram?
Dump grid.
Dump grid, exactly. And here, what do we put?
Grid.
Grid, exactly. Okay, which also, in my opinion, should be arg, but never mind. So the rest of that input would be filled in a very similar way. Okay, but that's the idea of calculating a histogram from multiple. So we're adding multiple kernels to that histogram on every step, rather than adding a single kernel when we do an input like that, which is cool. And then the rest of that will be available after this tutorial when I show you the exercises. So we've gone through everything there. Let's stop the share. Oh, there's a chat message. Great. So I will turn off the streaming now.